So yesterday we have seen what is topicity. So now I have a few problems. So we are going to solve those problems. So I hope these problems will help for your CSR examination point of view. And here the main thing is we have to know about the constitutional isomers, because these are the frequently these options will be there in the any question, like if they are asking a relationship between two hydrogens, then these are the four options you mainly see: enantiomers, diastereotopic, and then homotopic. Okay, so if a plane of symmetry is there, you just close your eyes, keep enantiotopic. If no symmetry is there, then that is diastereotopic. If CNX of symmetry is there, then that comes under the homotopic. So we'll take one simple example here. So here we have hydrogen, this is Ha, and this is Hb, and here we have methyl group. So the question is, so what is the relationship between Ha and Hb? So as I said, that if plane of symmetry is there, that is enantiotopic. We can pass a plane vertical to the, we can pass a plane like that. So we have a sigma plane of symmetry in this case. So because of that reason, this Ha and Hb belongs to the they are having a enantiotopic relationship. Okay, initially we will solve little bit simple examples so that it will be easy, and then we'll take this example here: CO, hydrogen and hydrogen. So now the relationship between this Ha and Hb. So here also we have a plane of symmetry. We can pass a plane like that, like this. So we'll be having two, we are getting it two different halves. So because of that reason, this in the second example, this Ha and Hb is having an anisotropic relationship. And then we have this example, here methyl and hydrogen, methyl, hydrogen. So in this case also we can see a plane of symmetry. Okay, now because of plane of symmetry, here Ha and Hb are having an anisotropic relationship. And similarly, in the examination point of, in the exam, they may ask about what is the relationship between these two methyl groups also. If these two are anisotropic, these two also anisotropic. Both the methyl groups CH3A and CH3B are anisotropic. Then we'll go for this example. This is Ha and Hb. So here also it's very simple. Here we have a plane of symmetry. We can pass a plane like this. So we'll be having a plane of symmetry. Because of plane of symmetry, these two are anisotropic in relationship. Okay, so further confirmation, if you need more further confirmation, anything, you can take any example, just replace this hydrogen by nucleophilic, some nucleophile. So let's take, we'll take bromine and hydrogen, and if we do this one, we get a mirror relationship like this. So these two are after replacement, so these two are having a mirror image relationship. So this way also we can say these two hydrogens having an anisotropic relationship. So same way you can do for anything, and you can also go through the RS nomenclature. Okay, so R and S, this comes in the enantiomers, R and R, S and S, R S, SR. So these all comes under anisotropic relationship. okay, because mirror image means like if R configuration is there in mirror image, it comes out to be S, like that. So if anisotropic means they should follow these rules, then it's very easy to identify. So either you can follow the symmetry criteria, or you can also follow the substitution criteria. And as I explained yesterday, if you want to identify the relationship between any two hydrogens, so you just need to follow two criteria. The first one is symmetry criteria. So symmetry criteria is a preliminary test. So by looking at symmetry, you can just get a confirmation whether it's enantiotopic or diastereotopic or homotopic. So if you need further confirmation, you have to go for the substitution method, or substitution or addition. Okay, if double bond is there, that addition. If no double bond, then substitution. So when we go by substitution addition method, then we'll get a further confirmation. So you can give RS nomenclature here also. So according to that, we can identify these two are having mirror image relationship, and these are enantiotopic in nature. And then so here we have OH, H and H. So in the yesterday's class, I have said already that if any hydrogens are adjacent to the chiral center, there belongs to the diastereotopic. So why there belongs to diastereotopic? So what is diastereotopic? They should not possess any kind of symmetry. So they will not show any kind of symmetry. So when we have a chiral center, in that case only C1 symmetry is possible. Other than that, nothing is possible. So because of that, if two hydrogens are there, they are adjacent to the chiral center, you don't need to go this anyway symmetry criteria. We will not see any kind of symmetry in diastereotopic. And even substitution method also, you no need to go, because it's already confirmed that chiral center is there, means adjacent to the chiral center hydrogens will be diastereotopic. And then so what about these two hydrogens? So here also it comes like these two are enantiotopic. Because a plane of symmetry is present in this. So here also we have a plane of symmetry. So you can for your convenience, you can write like this. So we can pass a plane like this. So we have a plane of symmetry. That's why these two hydrogens are enantiotopic in nature. And then we have another example where we have OH group here and hydrogen, then another hydrogen. Okay, so what is the relationship between these two hydrogens? So here we can see that I think it's some methyl groups. This should be here. Okay, so here we can see this is the chiral center. The hydrogens which are adjacent to the chiral center, they belongs to the diastereotopic. Okay, and then we have this compound. So now the relationship, we need a relationship between these two hydrogens. Okay, and when they ask this kind of questions, like mostly I will tell one simple thing to remember: the hydrogens which are adjacent to the carbonyl compound always, most of the times, enantiotopic. You can remember this. Okay, the hydrogens which are adjacent to the carbonyl group, always they are enantiotopic. And here also we can see a plane of symmetry, and for our convenience we can write this one like this. Here methyl group and a methyl group, here hydrogen and carbonyl group, and here we can pass a plane like this. So we have a plane of symmetry. So because of that reason, this is the enantiotopic in nature. So you can remember this one. almost means like I will not say exactly 100%, but if you don't know anything, it means if you're having problem like you're unable to identify what is the relationship, so you can that in that case you can use this method. Okay, and like this is mostly when we have only one carbonyl group. So when we have more than one carbonyl group, that time it may not be acceptable. Okay, so we have to remember that. Next we'll see this example. So here more than one carbonyl group is there. Here hydrogen we have, and this hydrogen and hydrogen. So in this case we have two hydrogens, HA, and as well as HA and HB. So here the HA and HB this one shows enantiotopic relationship, and these two hydrogens shows diastereotopic relationship. So here also you can just follow this method. So you will be seeing the plane of symmetry for these two hydrogens. For these two hydrogens you will not see any kind of symmetry. Like what I said here, what I mean that if only one carbonyl group is there, that time we can pick for enantiotopic. So when we have more than one carbonyl group, that time we can choose, means that time we cannot apply this one. And this I have a little bit doubt HA and HB, and I will check this example, and I will write in the comment box that what is the relationship between these two. And this example we just keep it aside. I also have a little bit doubt, and now okay, it will take some time, so I will clarify it after uploading this video. And one more thing, like when we have a hydrogens which are adjacent to the double bond HA and HB. So here also when we have this kind of relationship, we no need to go for any symmetry criteria, any substitution criteria, because here the compound which are having double bond, they gives a diastereomers. Okay, so that means these two hydrogens are having a diastereotopic relationship. Any hydrogens which are adjacent to the double bond, they are diastereotopic. So whatever the points I'm telling here, you just write down those points. It's very easy to if you don't know anything, then also it will be very easy to identify what is the relationship between hydrogens. And next we have this one, allylic these two hydrogens, what is the relationship? And you can draw a plane of symmetry here. So this comes under the enantiotopic. So when they will ask this kind of questions, so you can arrange them in this way so that you can easily identify whether plane is there or not. Next and these problems are very important. Okay, so what is the relationship between these two? So we know that benzene is having a C6 symmetry, okay, and also C2 also is there. So because of that reason, just if they are asking hydrogens on the benzene, you can remove enantiotopic relationship, that you can remove it. Okay, because your CNX of symmetry is there. Because of that reason, either it can be a homotopic or diastereotopic. Only these two options are left. because there is because of CN symmetry is there. So what is the criteria for homotopic? The CN symmetry is a criteria, right? So if benzene is there, means we can remove enantiotopic. Only two things are left, that is homotopic and diastereotopic. If the CN axis of symmetry is there, then homotopic. If no symmetry is there, then that is a diastereotopic. And here we can see a C2 axis of symmetry, this one here, this one here. So this comes out to be homotopic in nature. And now I'll discuss a little bit difficult problems. Methyl. So now we need to identify the relationship between these two methyl groups. So just don't get confused by the arrangement, what the way we have done. So you can write this one simply like this: methyl group and this carbon, and here like this you can write, right? So this carbon is this, and this one is this, and this carbon is this carbon, and CH3. And we can see a one, we can if you apply the symmetry criteria for this, if you rotate it by 180 degrees, so we will be having a C2 axis of symmetry here, right? We will be having a C2 this way. Okay, when C2 axis of symmetry is there, that comes out to be homotopic. So here these two methyl groups are homotopic in nature, and instead of above, if it is below, okay, so now it comes out to be like this: CH3, and here we cannot do a C2 symmetry. Okay, so this is not related to any kind of symmetry. So here we can't apply CN axis of symmetry, center of inversion, we cannot apply anything. So that's why when this is below the plane, this comes out to be diastereotopic. And we'll take same kind of problem. And this is above the plane, and this is also above the plane. And here is very easy, because we can pass a plane like this. So we have a plane of symmetry. So plane of symmetry is there, means what? Enantiotopic. And then this is the another one. Now we'll take both the methyl groups here only. So now this is an example. So we need to identify whether it is these two methyl groups are enantiotopic, or what is the relationship between these two methyl groups. So here also it's very easy. You just draw a line. So when they ask this Spiro compounds, so it's better to arrange these things in this way. Spiro compound means two rings are connected by one carbon atom, that is called Spiro compounds. When they ask Spiro compounds, if they ask for what is the relationship between any two groups, you can write them in this way, so that it will be very easy. And here this one I will write like this. Okay, now this is a methyl group, and this is another methyl group, and here I will pass a plane. So plane of symmetry is there. So plane of symmetry is there, means this is comes out to be enantiotopic. And then yeah, this is also. And what about these two hydrogens? So these two hydrogens are diastereotopic. So here we can also use chemical reaction. So this is coming from alkene. So we are doing a epoxidation. It's coming from alkene, that's why this is the diastereotopic. And now the relationship between these two hydrogens, and then this is another example. Remove it, methyl and hydrogen here, hydrogen here. So here we need to identify what is the relationship between these two hydrogens in this example, and here these two hydrogens, and here these two hydrogens. So first we see here, so here we cannot apply any symmetry element, so here no plane of symmetry, and CNX of symmetry also not there, because these same methyl groups are there, this type only hydrogens are there. So because of that, here we cannot apply any kind of symmetry, so this comes out to be diastereotopic, and this is also almost same diastereotopic, but here we can apply a CNX of symmetry, this angle. Okay, so because of that, this is a homotopic. Okay, and similarly when we have a benzene, so before I have said already, so when benzene is there, the most probable answer will be homotopic, because CNX of symmetry. So these hydrogens are homotopic in nature. So till now whatever examples I have said, I hope you understood. And then this sometimes what will happen is like so when we have this kind of examples, CH3, hydrogen and hydrogen, so here we will apply some substitution method. Imagine that we'll take some chlorine, so we'll replace hydrogen by chlorine. So here we have replaced chlorine and hydrogen. This is 1 2 3 4, and this is showing a R configuration. The second compound shows 1 2 3 4, it shows S. Okay, so it's supposed to be, these two hydrogens are supposed to be enantiomers, but these two are diastereomers in nature, diastereotopic. So because so we know that by NMR spectroscopy we can differentiate diastereomers. So when we have diastereomers, we'll get different chemical shift for diastereomers, and for enantiomers we can't identify. Enantiomers will be gives same NMR spectra, same chemical shift value, but diastereomers gives different chemical shift values. So because of that, these two hydrogens are having different chemical shift values, so because of that they are diastereotopic in nature. And another thing we can also say that means this is a better way to differentiate these two hydrogens by NMR spectroscopy. And I have one more example, this same example, same kind of example, and this one, this is HB and HA. So when we record a NMR for this compound, and these two hydrogens give same chemical shift values, that means if any hydrogens giving a same chemical shift values, they are enantiotopic in nature. So if they are giving different chemical shift values, they are diastereotopic in nature. And we have few more examples. So we'll take hydrogen is here, this is Br, Hg, HH, Hc, HF. So this is He, Hc, Hd, Ha and Hb. So now in this, so we have four pairs of hydrogens, right? So we have to identify what is the relationship between Ha and Hb, Hc and Hd, then He and F, HF, and Hg and HF, sorry, Hg and HH. And also we can see Ha and Hg, Ha and HH, and Hb and Hg, then Hb and HH, Hc and HF. Okay, so this is very easy. First we'll go for Ha and Hb. So from Ha and Hb, if this is hydrogen, okay, then all the hydrogens in this compound will be homotopic. Since this is not a hydrogen, since this is a bromine, so we can't say these are homotopic in nature, because bromine is there. Because of that, we can't pass a CN axis. Okay, so due to that, these halohydrogen should be heterotopic in nature. So heterotopic means we have two options: either it can be enantiotopic and diastereotopic. If any symmetry is there, then that is enantiotopic. If no symmetry, then that is a diastereotopic, right? So now here we have Ha and Hb. So do you think some symmetry element here we can apply? Here we cannot apply any kind of symmetry. We can see, we can draw a plane, so it cannot be same. Anyway, it is not same. So here we cannot apply any symmetry for Ha and Hb. So that's why these two are diastereotopic. And same Hc and Hd also we can't do anything. So these are diastereotopic. So similarly, HF and He also diastereotopic, and Hg, HF also diastereotopic. So now we have to identify the relationship between Ha and Hg. Okay, so when you are talking about Ha and Hg, so now I pass a plane like this, means here we are getting two equivalent halves, right? So now the Ha and Hg are having a enantiotopic relationship. These two are enantiotopic relationship. Similarly, Hb and HH are having enantiotopic. Okay, so similarly Hc and He and Hd and HF are having enantiotopic. So this is the way to identify which is enantiotopic and which is a diastereotopic in nature. And then, so what about the toluene? The hydrogens in this two hydrogens are homotopic in nature, because even if you substitute also, you will get same. You can't differentiate the compound, so that's why this is the homotopic in nature. And then we can draw this example: oxygen here, and here also oxygen, hydrogen and hydrogen. Okay, so this one, what is the relationship between these two? Here we have two hydrogens here, but this side only one hydrogen is there. So here we can't pass any plane of symmetry, is not there, but here we can do a CN axis of symmetry. So because of that reason, these two hydrogens comes out to be homotopic in nature. Okay, and when they ask this kind of questions in Narbonne systems, so anyway, most of the these compounds, these two hydrogens gives different chemical shift value. Okay, so that's why, means when two hydrogens are giving different chemical shift value, so we call them as a diastereotopic in nature. So that's why most of the compounds in these compounds are diastereotopic, because they give different chemical shift value. So this is about the enantiotopic, this is about the topicity. So, and I have already explained about the constitutional isomers. That's why I did not, in the last video I have explained about the constitutional isomers. So in this video I did not explain any examples of constitutional isomers, so it will be very easy only. Just the arrangement will be different. What I said yesterday, cyclopentane and this one. So these two are the constitutional isomers, same molecular formula but different connectivity will be there. So and this is about the topicity. I hope whatever the examples I have taken, I think it's clear. So if you have any doubts about these examples, you can write in the comment box. And if you like my video, please subscribe to my channel, and also please forward these videos to your friends. Thank you.